Hello, welcome to section 1.3. So section 1.2 and 1.3 are like really closely linked. So in section 1.2, basically the whole point of that section is to show you that if you want to find the slope of x squared, you can just use the equation 2x. So if you want to find the slope of x squared at the point x equals 1, it's just going to be 2 times 1. So this idea where you can have a curve and then there's a formula that will tell you the slope at any point is actually a derivative. So the formula for the slope of the curve f of x is called the derivative of f of x. So I'm going to write that and then kind of walk through it one more time. So the formula that gives you the slope of the curve of f of x is called the derivative of f of x. So it gets written like this with this little prime here, f prime of x. Sometimes people say f prime of x, like I just did. F prime of x. So put that quotes. It can also be written as like d over dx, like this little fraction. And the way that's said is the derivative with respect to x. The derivative with respect to x. Okay, and when we go through this process of trying to find the derivative or calculating the derivative, it's called differentiation. So I hope I'm not being annoying, but I find that it's very helpful to have things repeated. So I want to repeat one more time. A derivative is the formula that gives you the slope of a curve. So for example, probably the easiest one is if we were going to find the derivative of a constant function. So a constant function is something in the form like f of x equals a number, like f of x equals 1. So we'll just draw that straight line right there. So that's f of x equals 1. So it's always going to be a straight line. Oh, look, I already did one here. So this one is 1, 2, 3, 4, 5. This is f of x equals -5. And then let's do here. That's not my best straight line, but we'll say that's f of x equals 4. So these are constant functions. Notice that they're all just horizontal lines. So for each one, if I want to find the slope, I mean, I could pick 2 points and then, use my slope function. But if you remember, m is the change in y over the change in x. And the change in height is 0. So this is 0 over just some number. So the slope is 0. And I think if we went all the way back to section 1.1, this is something we know, that the slope of a horizontal line is 0. So what that's telling me is no matter what the constant function is, the derivative is always going to be 0. So the derivative of any constant function, if f of x equals b, so like a number like 1 or 5 or 4, then the derivative is f prime of x equals 0. So in other words, if you have a constant function, the slope of that constant function is 0, so the derivative is 0. And then we can get a little bit fancier, and we could do straight lines again, but let's do linear functions and figure out what their slopes are. So y equals 3x. If you go back to section 1, it's y equals mx plus b, and m is the slope. So this should be fairly easy. The slope of this first one is 3, and then 0.23, -130, and -0.1. So then this is a PDF, so there's like a gap here that doesn't need to be here, but that's because it's a different page. What letter represents slope in linear equations? We just talked about that. It's m. So the derivative of a linear function, if it's in the form if f of x equals mx plus b, then the derivative is just that m, because the derivative is telling you about the slope. So we've done a straight horizontal line, we've done lines with different slopes. So let's try something a little tougher. So I've got this graph here. This is x minus 1 squared. That's what this is. I'm going to draw a line. X minus 1 squared. And I'm going to pick a couple points. And so I was going to fill this part in right here, but let's skip it for now. We're going to skip that. So I'm going to try to find slopes of this curve. And I've got, got some ideas here on how to do that. So it wants me to draw a secant line through the points 1.5 and whatever goes there. So let's see, 1.5 up here. So I've got 1.5 and I need to find whatever this y value is. So I would do 1.5 and then I would plug it into my equation over here. So that's 1.5 minus 1 squared. Okay, so 1.5 minus 1 is just 0.5, and then 0.5 squared is 0.25. So this point right here is 1.5 and then 0.25. So I can fill that in below. So 1.5 and then 0.25. And then I want to find the secant line through the points 1.5, 0.25, and 2.5, whatever goes in there. So 2.5 is up here. Well, it's at 2.5 on the x-axis is right here, and it corresponds to this point that I need to find. So again, I'll plug it in. So 2.5 minus 1 squared. 2.5 minus 1 is 1.5. 1.5 squared. Let's see, I'm going to have to put that into a calculator. All right. 1.5 squared, that's 2.25. And that looks like that matches. That does look like 2.25 on the y-axis. So this is the point 2.5 and 2.25. Okay, so going back to the directions here. Let's fill this in. Draw a secant line through the points 1.5 and 0.25 and 2.5, 2.25. So if you remember, a secant line is just the straight line that connects those 2 points. So I'll do my best here to draw a secant line. Okay, it's not a great straight line, but I tried. So now that I've got that, I'm going to try to find the slope of that line. So calculate the slope of the secant line, because remember when we're trying to find derivatives, that's all about slopes. So m is going to equal y2 minus y1, or x2 minus x1, which would be 2.25 minus 0.25, that makes for easy math, and then 2.5 minus 1.5. Okay, 2.25 minus 0.25, that's just a 2. And 2.5 minus 1.5, that's just a 1. So I get 2. Interesting. So my approximation is that around here, around 1.5, the slope is around 2. It's close to 2. So to make it to get closer to what the actual slope is, I'm going to move my point closer. So I started with 1.5 and I'm keeping that the same. So 1.5, 0.25. And then instead of doing 2.5, I'm going to move closer. So 2.5 is right here. So I'm moving 1 closer. So I'm getting closer and closer to 1.5. So just like before, I'm going to figure out what this point is. So I know it's the point 2 and something else. So 2 minus 1, I'm plugging it in, 2 minus 1 squared. This is my scratch paper over here on the right side. 2 minus 1 is 1, 1 squared is 1. Okay, that checks out. So I've got this point right here is the point 2, 1. And now I'm going to draw a secant line between those 2 points. Sorry about how bad my secant lines are. But if you think about it, so I started with this point out here, and then now I'm choosing this point here. If I keep getting my points closer and closer and closer to 1.5, I could like keep zooming in. Eventually, that's going to be really, really close to the tangent line, which is what the slope actually is at 1.5. Well, anyways, I got ahead of myself. So I drew my tangent line. Now I'm going to do the slope between those 2 points. So draw a secant line through the points 1.5, 0.25, and 2, 1. Calculate the slope of the secant line. So m equals, looks like 1 minus 0.25 over 2 minus 1.5. So that's going to be 0.75 over 0.25. All right, I'm going to calculate that. Oh, I think I made him, yeah, my bad. It's 2 minus 1/2 is a half. My bad. I think I got that. Okay, calculator says that is 1.5. Okay, so let's go back to our picture. So this first secant line that I did, I'm going to call A. And then my second line I did B over here. So when I did A is steeper than B. So it makes sense that the slope of A is 2 and then the slope of B is just 1. But my goal isn't for a secant line. The equation for a derivative, it has to be the slope of the tangent line. So I'm trying to approximate the tangent line by making my secant lines closer and closer to a tangent line. All right, so my last bit right here says draw a secant line through the points 1.5, and we now know that's 0.25, and 1.75. So notice 1.5 and 1.75 are pretty close together. So let's go back up here. So now I'm choosing right in here. This is my x value. I want to figure out what that point is right there. So that point, and I'm actually going to label it down here, is, actually no, that looks pretty terrible. I'm going to label it over here. So this is, this became trickier than I thought. This point right here, I'm going to label right here, 1.75. And then I'm going to do my scratch work again. 2 minus 1.75 squared. And I'm just going to put this in my calculator. Let's see, when I do that, I get, 0.5625. Okay. So then this point right here is 1.75, 0.5625. So this point is super close to 1.5. So I'm getting much closer to the actual tangent line right there. All right, so I've got a bunch of secant lines. Now I'm going to calculate the slope. And I'll write in here, this is 0.5625. So slope is going to be y2 minus y1, 0.5625 minus 0.25 all over 1.75 minus 1.5. Okay, and then that is definitely something I want to put in a calculator because I am a little bit lazy. Okay, it looks like 1.25. Yeah, I'll put that into a calculator. So notice this number. So I started up here with 2, and now I'm getting a slope of 1.5, and then a slope of 1.25. So it seems like it's getting smaller and smaller and smaller, and maybe eventually it'll approach our tangent line. So which line approximate the tangent line the best? If you go back, so this line A, that was too steep, B was too steep, and so is C, but C is definitely the closest to being the tangent line. So the tangent line should look something like that. So C, or the one we did in part C, is the best. So line C. Okay, so now we're going to just try zooming straight in. So this curve over here, this is the same thing. This is still x minus 1 squared. They're all x minus 1 squared. It's just like zooming in closer and closer. So zooming in. Notice like, so see how this is like 1.3. This is, I mean, it's, oh, actually, oh, that's 1.5. I'm a little dumb. So we're zooming in on 1.5, obviously, I knew that. Look how close this one is. And this looks like a straight line. It looks like a perfectly straight line. So this is basically the tangent line. Going up like that, it's kind of nice. Got a very like even slope. Okay, so we could keep zooming in like this, but I don't want to like, well, let's do it. I sometimes over repeat things, but this is one of those problems that I think is really hard and it would be better to repeat. So now we're doing the same thing. We're going to draw a secant line through the point 1.5, and I believe we decided 0.25, and then 1.500001 on the previous page. But we're going to plug 1.500, let's see how many, 1, 2, 3, 4, 4 zeros into our equation to get the output. And that is almost certainly a calculator problem. Let's see, it ends up being 0.25 0001 0, well, there's a lot of zeros, 5, 1. So it's pretty close to just a quarter. It's pretty close to what that is. And I can't fit that in here, but I'm just going to circle it and say that goes right here. And then I'll find the slope. So m equals that terrible number, 0.250001 0000001, and then minus 0.25, and then 1.500001 minus 1.5, and then I'm going to put that into a calculator, and I get 1.000001. If you were going to round that, I bet you would round that to 1. So my question to you then is, what do you think is the exact slope of the tangent line at x equals 1.5? My hope is that you would say 1. So just to give you my argument one more time, you know, we got a slope of 2 over here, and a slope of 1/2, and then a slope of 1.25. And then when we like super zoomed in, we got a slope of 1.00001. To me, I think we could round to 1. That's my bet. So instead of answering part H, what amount of error is close enough to perfect in your opinion? So I think that's something to think about. In your opinion, does that round to 1? Is that close enough to 1 that you believe it? It counts to me, I think. All right, I think that's the end. Oh no, well, let's stop here. This is a lot to process. Please feel free to add any questions that you have to the Q&A discussion board, because this is probably like the biggest part of the class. This is like the biggest leap to get over. Well, anyways, post your questions. Bye.